My name is Shiri, and this video is about a paper on the hardness of dominant strategy mechanism design, which is joint work with Shahar, Dobzinski and Vondrak. So before we get into the details, let's start with the motivation. Consider the case where we have an apple and two players, Alice and Bob, and we want to give the apple to the player who wants it the most. In this case, Alice's value is 6 and Bob's value is 4. How do we do it? We give the apple to the highest bidder, which is Alice in this case, and we charge her the second highest bid, which is 4. Bob gets nothing and pays nothing. Therefore, her profit, which is equal to her value minus the payment, is 2, and Bob's profit is 0. By charging the winner the second highest bid, we get that players cannot increase their profit by misreporting their values. This guarantee holds for every possible combination of Alice's and Bob's values. Therefore, the payment functions PA and PB implement the function f. Whenever a function has payment schemes that implement it, we say that it is implementable. Now, let's consider two protocols that realize a second price auction. The first one is a serial protocol. In this talk, we will use the terms protocol and mechanism interchangeably. As you can see, Alice sends her value first, and then Bob sends his value. Given their values, we can easily tell who is the winner and what is the payment for each of them. Now, we say that the protocol is ex post incentive compatible if it realizes a social choice function together with the payments that implement it. This protocol realizes the second price auction, so by definition, it is ex post incentive compatible. Since it is ex post incentive compatible, the next question that comes to mind is whether it is also dominant strategy incentive compatible. We say that a mechanism is dominant strategy incentive compatible if each player has a dominant strategy in it. We will now get a sense of why Alice does not have a dominant strategy in this mechanism. To this end, consider the following irrational strategy of Bob. He ignores his value and conditions his behavior on Alice's message. If she sends 1, Bob sends 0, and for every other message that she sends, he sends 8. Assume that the value of Alice is 9, and note that she should bid 1 instead of 9 to maximize her profit. When bidding 9, her profit will be 1 because she pays 8. But when bidding 1, she wins the item and pays 0 for it, so her profit is 9. Therefore, bidding the true value is not a dominant strategy for Alice. In fact, for every possible strategy of Alice, we can come up with some strategy of Bob, such that Alice maximizes her profit by choosing a different strategy. Therefore, she has no dominant strategy, and the protocol is not dominant strategy incentive compatible. Now, to better understand the concept of dominant strategy mechanisms, let's see one. In this protocol, Alice and Bob simultaneously send their values. Then, the bidder with the highest value wins the item and pays the second highest bid. This protocol realizes a second price auction, so it is ex post incentive compatible. As for dominant strategy incentive compatibility, observe that Bob can no longer condition his message on Alice's. Therefore, we can prove that Bob has no strategies that dissuade Alice from being truthful, so the protocol is dominant strategy incentive compatible. In our work, we try to understand the gaps between the power of dominant strategy mechanisms and ex post mechanisms. For that, we will now describe the revelation principle, which is well known in the mechanism design literature. It says that given an iterative ex post mechanism for some function, we can use it to design a new protocol where all players simultaneously send their strategies in the iterative one. By that, we get a new simultaneous protocol for the same function, which is also dominant strategy incentive compatible. It immediately implies that dominant strategy and ex post mechanisms have the same power, because as we have just said, an ex post mechanism for a function can be used to construct a dominant strategy mechanism for it. But what about computational considerations? Is the power of communication efficient ex post mechanisms equal to the power of communication efficient dominant strategy mechanisms? Are there any optimization problems that can be efficiently solved by ex post mechanisms, but not by dominant strategy mechanisms? These questions are at the core of both the talk and the paper. Now, at first sight, it seems almost obvious for dominant strategy mechanisms to be less powerful than ex post mechanisms, since dominant strategy incentive compatibility is intuitively a much stronger requirement. However, if we look at two-player combinatorial auctions where the domains of the valuations are rich enough, we have that efficient dominant strategy mechanisms and efficient ex post mechanisms have the same power. In addition, the very first separation between dominant strategy and ex post mechanisms was only recently discovered. Thus, it is only natural to understand whether we can replicate this separation also for natural settings. Before we continue, let's go over some preliminaries. For most of the talk, we focus on the setting of combinatorial auctions. In a combinatorial auction, we have m heterogeneous items and n players, where each player holds a valuation function that specifies its value for every subset of items. We assume that the valuation functions always satisfy that the value of the empty bundle is 0, and that if one bundle T contains another bundle S, then the value of T is larger than or equal to the value of S. Now we care about the following optimization problem. For every valuation profile of the players, V1 to Vn, we want to output an allocation of the items that maximizes the sum of the values of all players from their bundles. We are generally interested in combinatorial auctions where the valuation sets of players are natural. The following valuation classes are considered natural. We show them now and we will refer to them later on. Now let's define formally the notion of communication protocol, or equivalently a mechanism. It is a tree where each internal node has a set of players that speak in it, a set of possible messages for each player, and mapping of the messages to the next node. For example, the simultaneous mechanism for the second price auction has one internal node, which is the root. The players that speak in it are Alice and Bob, and the set of messages of each player is 0 to 2 to the k-1. Each combination of two messages is associated with the next node, which is a leaf. The leaves are mapped to an allocation and payment, which are in this case a function that takes as input the messages and outputs the identity of the player with the maximum bid and the second highest bid. In this work, we use the blackboard model, which means that all players see the messages sent by all the other players. Now, for the sake of formally defining ex post mechanisms and dominant strategy mechanisms, we need to define the notion of strategies. A strategy of player I is a function Si that takes as input the valuation of the player and outputs which messages she sends in each node. For example, the truthful strategy in the serial implementation of a second price auction simply maps each valuation to its message in each node. Observe that the strategy does not have to be rational. For example, a possible strategy is ignore your valuation and always send 1. Or a possible strategy that is only possible for Bob in this protocol is ignore your valuation and condition your message on Alice's message. Send 1 if she sends 9 and otherwise send 72. Now we say that the mechanism is ex post incentive compatible if there exists a strategy profile S1 to Sn, such that for every valuation profile, the actions specified by the strategy profile form an ex post Nash equilibrium. In other words, no player gains by deviating from his strategy as long as all the other players stick to their strategies. This definition is equivalent to the definition that we have previously mentioned, that says that a mechanism is ex post incentive compatible if it realizes an implementable social choice function together with its payments. Similarly, a mechanism is dominant strategy incentive compatible if there exists a strategy profile S1 to Sn, such that for every valuation profile, the actions specified by the strategy profile form a dominant strategy equilibrium. It means that no matter what the other players do, it is not beneficial for any player to deviate from his strategy. Now let's see some examples. We remind that as we have seen before, the serial implementation of a second price auction is ex post incentive compatible, but not dominant strategy incentive compatible. We have also seen that the simultaneous implementation of the second price auction is both dominant strategy and ex post incentive compatible. Now observe another serial implementation of a second price auction. In the first round, Alice is asked whether she wants the item at price 0. If she does not want it, then Bob wins it at this price. Otherwise, Bob is asked the same question. Similarly, if he does not want the item, then Alice wins it at price 0. We continue with this iterative mechanism until one player quits, and then the other player pays his threshold price. It is clearly ex post incentive compatible because it implements a second price auction. In addition, it is also dominant strategy incentive compatible, because quitting while you still want the item is never beneficial, no matter what the other player does. Therefore, all players have a dominant strategy. Now let's observe another mechanism. In this dictatorial mechanism, Bob sends one bid that says whether Alice wins the item or he wins the item, where they both pay 0. It is clearly dominant strategy and therefore also ex post incentive compatible, because the dominant strategy of Bob is to just take the apple if he has some value for it. For Alice, she says nothing at all, so she trivially has the dominant strategy as well. However, this mechanism does not approximate the social welfare. It could be that Alice's value is much larger than Bob's value, but he still wins the item. Most research to date has focused on understanding whether communication-efficient ex-post mechanisms are less powerful than communication-efficient non-incentive compatible protocols. So, what do we have so far? We know that for the class of cross-substitutes valuations, there are efficient protocols that obtain the optimal welfare. Thus, by using VCG payments, we get ex-post mechanisms. For submodular, XOS, and subadditive valuations, we have that non-incentive compatible protocols achieve at least half of the optimal welfare. In contrast, efficient ex-post mechanisms achieve only a sublogarithmic fraction of the welfare. Therefore, there are huge gaps between the known lower bounds and upper bounds for ex-post mechanisms. Despite that, there is only one result that shows an inherent separation between ex-post mechanisms and non-incentive compatible protocols. It says that no efficient ex-post mechanism achieves a fraction of more than 3/4 minus 1/240 of the welfare. In contrast, there exists an efficient non-incentive compatible protocol that achieves 3/4 of the welfare. Interestingly, most of the ex-post mechanisms that achieve the state-of-the-art are in fact dominant strategy mechanisms. This is another reason to study the hardness of dominant strategy mechanism design. Here are the results, which are divided into 3 categories. Hardness of exact welfare maximization of dominant strategy mechanisms for restricted classes of valuations. Hardness of approximation of dominant strategy mechanisms for general valuations. And hardness of approximation of simultaneous protocols. Now, our first theorem says that the communication complexity of every normalized dominant strategy mechanism that maximizes the welfare is at least exponential in M, where M is the number of items. In contrast, if we settle for ex-post mechanisms, then the optimal welfare can be computed efficiently. Before we continue, there are 2 terms here that I need to explain. When we say that a mechanism is normalized, it means that if a player gets no items, he pays 0. As for the definition of cross substitutes, we will not state it. The reason for it is that it is a very delicate definition, and it is not relevant for the talk. Given this lower bound, it is only natural to wonder what is the known upper bound for dominant strategy mechanisms with cross substitutes valuations. Observe that the best dominant strategy mechanism to date provides a square root of M approximation to the welfare. Therefore, the known upper bound and the known lower bound are very far apart from each other. It could be that there exists a dominant strategy FP for cross substitutes, and it is also possible that the square root of M approximation is all we can do. Our next theorem is in the setting of multi-unit auctions, so let's introduce it. In this setting, we have M identical items and N players. Yet again, we assume that the valuations are normalized and monotone, and similarly to combinatorial auctions, our goal is to output an allocation that maximizes the social welfare. In general, communication protocols are considered efficient if their total communication is polylogarithmic in the input size. In a multi-unit auction, each player holds M log M bits. Therefore, we look for protocols where the number of bits is polylogarithmic in M. We are going to focus on valuations that satisfy decreasing marginal values. It means that the marginal value of the first item is larger than the marginal value of the second item, which is larger than the marginal value of the third item, and so on and so forth. Now we are finally ready to state our results for a multi-unit auction with decreasing marginal values. We have proved that every normalized and dominant strategy mechanism for this setting satisfies that its communication complexity is at least M log M. In addition, we proved that this lower bound is tight. There exists a dominant strategy FP mechanism for this setting. We will now explain how this hardness result is related to the hardness result of exact welfare maximization for cross substitutes in a combinatorial auction. Now, observe that additive and unit demand valuations can be represented very succinctly, both in the combinatorial auction and in the multi-unit auction settings. Therefore, the optimal welfare can be obtained by a trivial simultaneous protocol, which is dominant strategy incentive compatible and therefore also ex-post incentive compatible. In contrast, the optimal welfare for the class of decreasing marginal values is obtained by an iterative binary search protocol. Once we have the optimal allocation, we compute VCG payments to obtain an ex-post mechanism. For gross substitutes, the optimal welfare can be obtained by an ascending auction, which is also followed by the computation of VCG payments for ex-post incentive compatibility. We have shown that for both these settings, which require a smart optimization procedure, we have that the optimal welfare cannot be obtained by dominant strategy mechanisms. Therefore, both results boil down to the following general statement. If the optimal welfare requires smart optimization, then it is hard for dominant strategy mechanisms. Now let's move to our next result, which is about hardness of approximation for dominant strategy mechanisms. The theorem says that achieving an approximation ratio better than m requires exponential communication. Note that this result is tight because if we run a simultaneous second price auction on the bundle of all items, then we get an efficient, dominant strategy mechanism that m approximates the social welfare. The proof outline is as follows. We begin by showing that every simultaneous randomized protocol for general valuations with approximation better than m requires exponentially many bits. Then, in the second part of the proof, we show that if we have an efficient dominant strategy mechanism that gives an approximation better than m, we can use it to construct a simultaneous protocol with roughly the same approximation ratio. Now, an immediate corollary of this theorem is that randomized dominant strategy mechanisms are more powerful than deterministic dominant strategy mechanisms. The reason for it is that by the theorem above, there are no deterministic mechanisms with approximation better than m. However, there exists a randomized universally truthful mechanism that gives us square root of m approximation. Now we conclude by stating two hardness results for simultaneous protocols. The first theorem says that the communication complexity of every simultaneous protocol that gives an approximation better than m for general valuations is exponential in m. Observe that we have already stated this theorem because it is the first step in the proof of hardness for dominant strategy mechanisms. The second theorem says that the communication complexity of every simultaneous protocol that gives approximation of m to the power of 1 over 16 for gross substitutes is exponential in m. By that, we answer an open question of Dobzinski, Nissan, and Oren. We will now present avenues for future work. The first one, which we have already mentioned, is closing the gap between the lower bound and the upper bound for dominant strategy mechanisms with gross substitutes valuations. In addition, we have managed to show hardness only for deterministic dominant strategy mechanisms. I think that studying the power of randomized mechanisms would be very interesting. And that's it. Thank you very much for listening.